Okay, this is video 5 in our course on basic circuit analysis, and in this video we're going to continue with nodal analysis. Nodal analysis, so this is part 2. Part 2, and the previous video is a requirement. Do not watch this video unless you have a good handle on video 4, Nodal Analysis Part 1. Alright, so in the previous video we said we were only looking at circuits without voltage sources. And so in this video we'll address nodal analysis with voltage sources. And so I'd like to take kind of an intuitive approach to understanding why voltage sources change the method here. And so I'd like to call your attention to this circuit. So first of all, remember we set up n-1 equations. So let's first, where n is the number of nodes. So let's first identify all of the nodes. So there's this one, this one, this one, and this bottom one down here. Okay, and remember that one of the early steps of the procedure was to call whichever node you'd like to be ground. So I'll call this one to be ground down here. And that means that this node, if you want to call this node 0, that's at 0 volts. And we would label these nodes. We'd label this node as 1, so we'll call this voltage V1, and we'll label this node up here 2, so we'll call the voltage there V2, and maybe this guy is 3, so we'll call the voltage at that node V3. Okay, and if you followed the last video, then we said, again, there are n-1 equations that we would need to set up, and there are n-1 unknowns, and, namely the node voltages. So here we have n equals 4 nodes, n equals 4 nodes, and so previously we would say we needed n-1 equals 3 equations and unknowns. And we would write those equations in a matrix form and use reduced row echelon form to solve that. Well, the unknowns are the node voltages, and by definition the voltage sources actually fix the voltages between nodes. So if our unknown voltages, or if our node voltages are the unknowns, and the voltage sources are telling us the relationship between those unknowns, then the voltage sources, in some sense, are helping us. And what I really mean is that the voltage sources are actually decreasing the number of equations we need because we know the relationships between the node voltages. So for example, if we called this guy 0 volts down here, which we did because of ground, and this 10 volt source is between nodes 1 and 0, that is, node 1 is 10 volts higher than node 0, and this is 0, then that immediately means that this voltage up here is 10 volts. Alright, and now all we need then, well, we know the relationship between nodes 2 and 3, okay, but we know that V3 is 5 volts higher than V2, but we don't know V2 and we don't know V3, so now we're kind of stuck. Okay, so we notice we're going to have to make some sort of adjustment to this, okay, because this now V1 is no longer an unknown. We only have V3 and V2 as unknowns, and further we know the relationship between them, namely V3 is V2 plus 5 volts. Okay, now whenever I have a voltage source, or let's just continue with the procedure outlined in the previous video. So let's just guess the directions of all of the branch currents. So let me call this I1. And I'll guess this guy is going to the right, I2. And we're going to keep doing this, and you're going to see a problem that's going to arise. I3. This branch current is I4. Okay, this branch current is I5. Now, let's try, and I say try, emphasis on try, to write a KCL equation at node 3. Okay, so KCL at node 3. Now remember, we're going to write the unknown currents in terms of the unknown node voltages. So at node 3, I do have I2 entering, okay, and I have I1 and I4 leaving. So this is what my KCL equation would look like. That's fine until we get to the step where we're supposed to express these guys in terms of the unknown voltages. I2 is okay. I2 is 10 volts minus V3 over 2 ohms. No problem there. I1 is okay. That's V3 minus 0 over 8 ohms. Okay, the problem is I4. How am I going to express I4 in terms of V3 and V2? And the answer, that's a rhetorical question. The answer is you can't. This guy came from Ohm's law, right? Ohm's law. That equation, it says the current through a resistor is the voltage across divided by the resistance. This guy came from Ohm's law as well. The current through, I1, is the voltage across divided by the resistance. Okay, we can't use Ohm's law here for I4 because Ohm's law applies to resistors, and this is not a resistor. So we're stuck. See? We have no way of expressing that current. And so we need a slight modification to the previous video's procedure. So let me delete this work here. And what I'm going to do is I'm going to take the two non-ground nodes that are separated by the voltage source. So V3 and V2 are not grounded, and there is a voltage source between them. So what I'm going to do is instead of making two separate nodes, V3 and V2, and yes, those are in fact nodes. I'm not going to change the definition of nodes on you. That those two are definitely nodes. What I'm going to do is kind of combine those two nodes into one node in purple here. One big node in purple. There's my node. Now, the purple glob, okay, well, it still must be true that however much current goes into it leaves it. Okay, it's just you know, it's a glob. It's not producing current. It's not absorbing current. Okay, so however much flows in still must flow out. So we can still write a KCL equation, and we're going to, right? But first of all, I want to make a definition. We're going to call this thing in purple a supernode. Supernode. Okay. A supernode occurs, or we'll say a supernode is the combination of two non-grounded ground nodes is separated by a voltage source. And that voltage source can be either independent or dependent. Here we have an independent voltage source of 5 volts. So there's my supernode. And notice then the voltage source for which we had a problem writing the current is in that supernode now. And again, I'm going to emphasize this relationship here, that V3 is V2 plus 5. So I'll write that in my picture. V3 is V2 plus 5. So now, it's because I know the relationship of those two things, whenever I'm going to write V3, whenever I would write V3, I'm going to write V2 plus 5 instead. So V2 is my unknown here, and it's my only unknown. Right? Observe. KCL at the supernode. KCL at the supernode. Okay, so this thing in lavender, I guess, is my supernode. So I have I3 entering the supernode. I have I2 entering the supernode. Oops, excuse me. So I3 is entering, plus I2 is entering. I have I1 leaving, and I have I5 leaving. Notice now, I4 is no longer in my equation, okay, because it got enveloped into the supernode. That's good because I can't write an expression for I4. But I can for these guys. So now I will continue on with that procedure detailed in the previous video. So I3, an equation for that, remember this guy's 10 volts over here. So this is 10 volts minus the unknown voltage, V2, divided by 4 ohms, plus I2 is this guy here. That is 10 volts minus, now instead of writing V3, I'm going to write V2 plus 5 because I have the relationship between them. Right? Here's the relationship between the two. V2 plus 5 volts over 2 ohms equals I1. So I1 is V3 minus 0, but instead of writing V3, I'm going to write V2 plus 5 volts minus 0 over 8 ohms plus I5 is here. Okay, I5, that's V2 minus 0 over 6 ohms. So there is my KCL equation at the supernode, and I've circumvented this problem of writing an equation for I4. So now let me simplify this a little bit by multiplying by the common denominator of 24 ohms. So this gives me 60 volts minus 6V2 plus 100. So if I do the 10 volts minus 5 volts, that's 5. So this will be 30 volts. And I have a minus V2. Oh, excuse me. So I'm multiplying everything by 24. 24. So yeah, I have 10 volts minus 5 volts. So that's 5. And times 6. Yes, 5 times 6, 30 volts. Okay, I have a minus V2. So that is minus 12 V2 equals, I've got a 3 V2 plus 15 volts plus 4 V2. So that's what I get when I multiply everything by 24 ohms. So this is one equation with one unknown, so I can solve this for V2. So I'll put all my common terms on the left, or constant terms, excuse me, on the left. So I've got a 60 volts, 30, that's 90. I bring 15 to the other side, so that makes 65 volts, I believe. 75, excuse me, 75 volts. Equals, and then I've got, on the right, I've got 4V2 and 3V2, that's 7V2. When I bring the 12 over, that's 19V2, and when I bring the 6 over, that's 25V2. So that works out nicely. That means that V2 is equal to 3 volts. Okay, so I'll add that to our picture. So now I know that this is 3 volts. So what does that make V3? Yeah, 8 volts. So I'm going to erase this guy. 8 volts, because there's a voltage source separating the two of 5 volts. So as soon as I know one, I know the other. 8 volts there. Alright, so you see, we solved this circuit only using one equation and one unknown. So actually, the number of equations we need is equal to not n minus 1, but n minus 1 minus nv, where nv is the number of voltage sources. And n is the number of nodes. Okay, this makes sense. Remember how we argued at the beginning of this example, where the voltage sources help us. So the more voltage sources we have, the less complex, or the fewer number of equations we need. N minus 1 minus NV. Alright, so I want to take a look at another example. So I'm going to clear this. Okay. Alright, so let's say we have a 14 volt source connected to a 4 ohm resistor and a 3 ohm resistor there. And then maybe we have another source up here, voltage source. And it's 6 volts. And we have a 2 ohm resistor and a 6 ohm resistor. And the question is about, here's V, and here's I. So the question is, find V and I. Alright, so first of all, let us identify all of the nodes. There's 1, there's 2, there's 3, there is 4. So how many equations will we need for this circuit? Well, number of equations equals 4 nodes minus 1 for ground minus the number of voltage sources, which is 2. So 4 minus 1 minus 2. We'll just need one equation. All right. So maybe in this problem, even though we're not talking about combining resistors, maybe you see that the 2 ohm and the 6 ohm resistors are in parallel. So we can combine those. When you have two resistors in parallel, you get the product over the sum. So that would be the product is 12 and the sum is 8 ohms. So that's 12 over 8. There's a 4 there, so that's 3/2 ohms. Okay, so we can redraw it if we like. So I'll do that. Four ohms. And it's good that we're doing this because I do want to illustrate a point about I now once you've combined the resistors. So we have 3 ohms, 3/2 ohms there. Okay, V, the unknown, is still right there. Okay, but where's I now? Where's this red I? Is it here? No. I is the current through the 2 ohm. This current is the current through the 2 ohm plus the current through the 6 ohm. So that's not what we're looking for. When you combine parallel resistors, you lose the information of the current. That's okay. Okay, it's like taking one step backwards to take 2 steps forward. We're still going to be able to analyze this simpler circuit and relate back to the original, as you will see. So again, here are the nodes. The nodes are still preserved when you combine parallel components. Okay, so in the original figure, if we called this 0, 1, 2, 3, then this is still 0 here. 1, 2, 3. See? The parallel resistors were connected between 0 and 3. 0 and 3. So the parallel combination is connected between 0 and 3. Alright, so we're going to choose one node to be ground. Let's do this one. Then node 1 has a voltage of 14 volts. We don't know the voltage at 2, and we don't know the voltage at 3, but we know their relationship. The voltage at 3 is 6 volts higher than the voltage at 2. So we'll call V2 to be the unknown, and then over here is V2 plus 6. And then here is my supernode. Supernode. A voltage source separating two non-ground nodes. Alright, we'll label the currents I1, I2, I3. And we'll do KCL at the supernode. Alright, so I've got I1 entering, and I2 and I3 leaving. So now we need to write those currents in terms of the unknown voltages. So I1 is 14 minus V2 over 4 ohms equals I2 is V2 minus 0 over 3 ohms plus I3 is this voltage up here, which we're calling 6 plus V2 over 3/2 ohms. Okay, and so I will multiply everything by the common denominator, which is 12. 12 ohms. So this is 42 volts minus 3V2 equals 4V2. Then when I multiply 12 by 3 halves in the denominator, that's like 8. So I've got 8V2 plus 48 volts. So again, I have one equation and one unknown, right? That's what we predicted up here. And so I will get the constant terms to the left. I've got 42 volts, and if I subtract 48, okay, I've got minus 6 volts. And then on the right, I've got 12, and then I bring over the 3. That makes 15 V2. And so that implies that V2 is minus 6 over 15. There's a 3 there, minus 2 over 5 equals minus 0.4 volts. Okay? So in the original figure, here's V2. That's negative 0.4 volts. Okay, and the problem was to find V, which was the voltage across the resistor, measured from this side to this side. So this is what we're calling ground, and we just found that this is minus 0.4 volts up here, so that is in fact V. V equals negative 0.4 volts. We've got half of our answer. Now, in the original figure, the node voltage at the voltage at node 3 is 6 volts higher than whatever we found at 2. So that immediately implies then that the voltage here is 5.6 volts. Because if I take 5.6 and I drop by 6 volts, I'm at negative 0.4. Said another way, if I'm at minus 0.4 and I raise by 6 volts, I'm at 5.6. Alright, well, I have all the voltages now, and I can get I equals, okay, from Ohm's law, V3 minus 0 over 2. So that's 5.6 volts over 2 ohms. Okay, so that is what? 2.8 amps. Supernode. Supernode, ladies and gentlemen. Okay. Let's work one more example. Or no, let's do two more. Okay, I'm going to delete this. Right. Let's say we have 10 ohms here in parallel with a 2 volt source. And then we have a 4 ohm resistor here and a 7 amp source, a 2 ohm resistor here, and a 2 amp source here. Alright, and we want to just kind of, without any specific directions, solve the circuit. So I need to find the voltage everywhere and the currents everywhere. And let's say that this is ground down here. Alright, so we'll identify the nodes. Here's 1. Here's 2. Here's three nodes. Right, so how many equations do we need? Number of equations that is the 3 nodes minus 1 for ground minus 1 voltage source equals 1 equation. Alright, well, I have a voltage source that is connected between 2 non-ground nodes. So that is going to make a supernode. So this whole thing here is a supernode in purple. Okay. That is a supernode. And the voltage right here, if we call this node 0, this is node 1, so we'll call this V1. And the voltage here, V2, is 2 volts higher than the voltage at V1 because of the power supply, the voltage source there. So this is V1 plus 2 volts. So whenever we use the voltage here, we're not going to use V2, we're going to use V1 plus 2 volts. Alright, and now let's label and guess the currents. Say this is I1, this is I2, and this is I3. Now, I want to start at the supernode. Actually, that's the only equation we need to set up. KCL at the supernode. Okay, and something interesting happens regarding I3 here. So we have the 2 amps entering, okay, the purple. We have I3 entering the purple. But we also have I3 leaving the purple. And we have I1 leaving the purple, and I2 leaving the purple, and the 7 amp source leaving the purple. So what do you notice about I3? It drops out, and it does not affect our equation, and it doesn't affect the circuit results. So what we say is we're going to kind of put that 10 ohm resistor inside our supernode, believe it or not. And the reason we can do that, this is the mathematical reason, because it drops out. Physical reason is because the 10 ohm resistor is in parallel with that voltage source that's in the supernode. So anything in parallel, if we had another resistor up here that was in parallel, that resistor could also be inside the supernode. Okay, so now our equation, now if we look at this messy thing here, you can see that yes, the 2 amp is entering, and these 3, I1, I2, 7 amp is leaving. Okay, so that's what we have here. 2 amps equals I1 plus I2 plus 7 amps. Alright, so let me rewrite those currents in terms of the unknown voltages. So I1 is V1 minus 0 over 2 ohms. V1 over 2 ohms. Plus I2 is the voltage here over 4 ohms. And we're not going to write V2, we're going to write V1 plus 2 volts over 4 ohms. And then plus 7 amps. Alright, so I'll get the constant, or I'll multiply everything by the common denominator of 4. So this is 4 ohms, so this becomes 8 volts. 2V1 plus V1 plus 2 volts plus 28 volts. Get the constant terms to the left, so this becomes minus 20 volts equals 5 V1, no, excuse me. I've got the 2 volts here and the 28 volts, so that makes 30, and when I subtract it, I get minus 22 volts. Yuck. Equals 3V1. So V1 is equal to minus 22 over 3 volts. Okay, so that's our answer. And that is approximately negative 7.33 volts, right? So that's the voltage here. I'll write it in our figure. Negative 7.33. Now don't be thrown off by the negative sign. All that means is that this node is lower than our ground, so we should have chosen this to be ground. Now the 2 volts separates this node and this node, so V2 is 2 volts higher. So this is negative 5.33 volts. Okay, and this is 0 volts down here. So we've got all of the node voltages. Okay, we could use Ohm's law to get the currents. For example, if I wanted I1, that would be the voltage here, negative 7.33 volts minus 0 over 2 ohms. Okay, so that's approximately negative 3.66 volts, I think, amps, excuse me. It's all right. 3, 1, 6, 8. Yes, that's correct. Okay. So don't be thrown off by the negative. The negative here just means we guessed the wrong direction. The current is in fact going up in that 2 ohm resistor. Okay, if I wanted I2, that would be the voltage here, which is negative 5.33 volts, minus 0 over 4 ohms. Okay, so that is negative 1 point, then we have a 12, so that would be 3 amps. Okay, and if we wanted I3, that'd be the voltage here on the left minus the voltage on the right. Divided by 10 ohms. So that is negative 0.2 amps. Right? Suppose we wanted the current through the power supply, or the voltage source. I'll draw that in green. Let's make it darker green. Let's say we wanted this current, I. Call it IX. Okay, well, we can't write an equation for that current, but I can do Kirchhoff's current law right here if I wanted. So now we would have this 2 amp comes into that junction equals I1 leaves plus IX leaves plus I3 leaves, and we've already found I1 using Ohm's law. We've already found I3 using Ohm's law, so we can solve this for IX, getting the current through the voltage source. So therefore we have all the currents, we have all the voltages, we can get powers if we want, and so forth. Okay, and I have one more example for you that I'd like to run through. And this one is different because it involves a dependent voltage source. So all of this analysis still applies with dependent sources as well. So let's say we have a 20 volt source there. Six ohms. And we'll say this is 3 Vx, and Vx is right here. Four ohms, 10 amps, and 2 ohms, and 1 ohm. Okay. And so the goal, again, we'll just keep it general. The goal is to solve the circuit, meaning find the voltages everywhere, find the currents everywhere. All right, let's call this guy ground. Right here. And I guess it doesn't hurt to identify the nodes, so we'll do that. Here's 1, here's 2, here's 3, here's 4, here's 5. 5 nodes. All right, we'll label them. 0, 1, 2, 3, 4. All right, how many equations will we need? How many equations will we need to solve this circuit? Well, we have 5 nodes, minus 1 for ground, minus 2 voltage sources. So that leaves us 2 equations here. We'll need 2 equations and 2 unknowns. So, what are those unknowns? Well, I have 2 voltage sources connected to non-ground nodes, this guy and this guy. So that makes nodes 1 and 3 a supernode. We'll call this supernode 1. Okay, and just as before, I'm going to call this guy V3. That's going to be an unknown, V3. So the voltage right here at this junction, okay, that's our unknown, and then the voltage here at node 1, okay, look at the light blue, the voltage at node 1, that's not an unknown, that's going to be V3 plus 20 volts. V1 equals V3 plus 20 volts. Here. All right, and now I have this guy, this voltage source. Yes, it's a dependent source, okay, but it's still going to be a supernode. So in purple, okay, we'll call this supernode 2. All right, and again, I'm going to call the voltage here at node 2, that's going to be my unknown. And the voltage at 4, V4, that's 3Vx. So I'm running out of space here, so I'm going to write it right here. V4 is V2 plus 3Vx. Okay, so V2 is my unknown, but whatever voltage that is, if I raise by 3Vx, that's going to give me the voltage here. Well, I don't want to write Vx, I want to keep it in terms of my unknown voltages. But I'll note that Vx is the voltage from 1 with respect to voltage 2. And 1 is V3 plus 20. So Vx is V3 plus 20 minus V2. So I'll plug that in here. And I'll note that V4 then is V2 plus 3 times V3 plus 20 minus V2. And if I combine some things here, I have a V2 minus 3V2, so that's 3V3 plus 60, and then a V2 and a minus 3V2 minus 2V2. Okay, again, that is V4. Okay, so my unknowns here, remember, I can only have 2 of them. If I have more than 2, I won't be able to solve it because I'm only going to have 2 equations. So my unknowns here are V3 and V2. Okay, so when I use KCL, I can only use V2 and V3, nothing else. No VX's, no V1's, nothing other than those 2 guys. Alright, so let's do KCL at supernode 1. Oh, and first I have to guess the directions of the currents. So we'll call this I1, call this I2, I3, I4, I5. Alright, so KCL at supernode 1, I've got, what do I have entering this purple blob? Just the 10 amps. And I've got I1 leaving, I've got I2 leaving, I've got I3 leaving. Alright, now let's write the currents in terms of our unknowns. So remember, V2 and V3 are our unknowns. So I1 is the voltage at node 1 divided by 2 ohms, but we're not going to write V1, that's not an unknown. We're going to write V3 plus 20. Then divided by 2 ohms plus I2. I2 is the voltage at V1 minus voltage V2. But again, V1 is not an unknown. We're going to write V3 plus 20 minus V2. V2 is okay because that's what we settled on as the unknown. Divided by 3 ohms plus I3. So that is V3 minus V4. But I'm not going to write V4, that's not an unknown. Instead, I'm going to use this equation that we derived. V4 is that guy. So V3 minus 3V3 plus 60 volts minus 2V2. Okay, and then all of that divided by 6 ohms. So let's get rid of the fractions by multiplying by 6 ohms. So here I have 60 volts equals 3V3 plus 60 volts plus 2V3 plus 40 volts minus 2V2. Then over here I have plus V3 minus 3V3 minus 60 volts plus 2V2. Alright, so I can work on this a little bit. The 60 volts and the 60 volts cancel. I've got a 40 and a minus 60. So that makes minus 20, and I move it to the other side so I get plus 20 volts. I've got a 2V2 and a minus 2V2, so they're gone. So I'm left with only V3s. That's nice. 3v3, and 2 is 5, and 1 is 6, minus 3 is 3. So this implies V3 equals 20 over 3 volts. And that is about 6.67 volts. Okay, good. So we can add that to our figure. This was V3. Well, I'm kind of out of space here, but that's the voltage right here. 6.67. Then the voltage at node 1 is 20 volts higher than that. So this guy is 26.67 volts over there. Alright, but what about over here at supernode 2? Well, let's do KCL there. KCL at supernode 2. Alright, what do I have coming in to that purple blob? I've got I2. I've got I3. What do I have leaving? I've got I4 and I5. Alright, so now I need to express these currents in terms of the unknowns, V2, V3. So I2 is the current that goes from here to here. So that is actually 26.67 minus V2 over 3 ohms plus I3 is this current here. So V3 is 6.67 minus V4, right? But V4 was this stuff. V3 plus 60 volts minus 2V2, and all of that over 6 ohms equals I4 plus I5. So I4 is the voltage at node 4 minus 0 over 4. So V4, but V4 is this thing, 3V3 plus 60 volts minus 2V2 over 4 ohms. And then I5 is the voltage here, which is V2, which is our unknown, over 1 ohm. Okay, I'm going to erase the supernode 1 and just kind of keep the result. The result was that V3 was 6.67 volts. Okay, so let me erase this, give us some more space. Alright, the common denominator here is 6. No, common denominator is 12, unfortunately. Yeah, I don't know that it would be worth the class time to do the math to figure this out. Let me just describe how you would solve this. So we have V3 from the work that I just erased. So this guy is 6.67 volts. This guy is 6.67 volts. So that leaves us just this equation in terms of V2. So that's one equation and one unknown. You solve that for V2.